Hello everyone, this is Amir Lisawi, your classmate from ICM. Today I'm going to help you with minimum and maximum values. Obviously a 1500 topic, you might have gone through it already, but I'm trying to help you today in case you have any problems. Anyway, so in this unit we're gonna try to identify minimum and maximum values as the slide says. So what are minimum and maximum values? Without looking at this slide, I can tell you as just a hint or a conceptual, let's say, conceptual point. A minimum maximum value usually always occurs at extrema points. So a extreme point at the edges of a graph or extreme points at, let's call them hills or valleys of a graph. So when you're thinking extreme points, think edges of a graph or hills in a graph. I will show you what that actually means in a little bit. So when I'm talking hills and valleys and edges of a graph, what do I mean? I mean critical points, local maximum minimums, and absolute maximum minimums. So let's go through them one by one. So critical points. Critical points, as the slide says, a number C in a domain, so the domain you're working with. C is a critical point in the domain when the derivative of your function is equal to 0 or the derivative of your function does not exist. So when the derivative of your function equals 0 or when your derivative doesn't exist. So remember me saying valleys or hills. Critical points occur when you have let's say, a straight line or a top up or a valley, basically. Because at hills and valleys, for you to start changing direction in a graph, you're going to zero out when it comes to the gradient. So that's when critical points occur. Again, I'm going to show you this, but this is just some theory. Local maximum minimums is the next thing that we need to take care of. Let me read this out. A local max or min, C, is an extreme point in an open interval. That's a typo. Around the point. So you have a point C. If you look at point C and you realize, oh, this point is extreme for all the values that are around this point. Okay, so if I have some point on a graph and you look at it and you're like, oh, this point is smaller than every other point around it, or this point is larger than every other point around it, it most likely is a local maximum minimum. Again, I'll show you. So the actual definition is x equals c, c being the local min or max, if f of x, which is the value of y, is smaller than f of c. So this is for the maximum. So if f of c is larger than every f of x around it, then it's most likely a maximum value. So let's continue here. I'm kind of chasing. X equals c if f of x is smaller than or equal to f of c for every x in an interval around the point c. And vice versa for min. You just flip the inequality. That makes sense? Again, I'll show you. Absolute maximum and minimum, final point that we have to tackle. On the other hand, an absolute max or min, C, is the extreme point in the whole working domain. So if you see a point and it's obviously the smallest value of y or the largest value of y in an extent of the whole graph. So you look at the graph between the working domain that you have, like the working interval or domain that you have, and you see a point and it's the largest or the smallest when compared to all the y values, then it's obviously a absolute maximum minimum. Like it should be obvious to you, the fact that it's the largest number, the smallest number. One point. An absolute maximum can be a local maximum. A local maximum can be an absolute minimum. So they're kind of interchangeable, but you'll see as you do more example how that works. So let's look at the definition. X equals C, C being an absolute maximum in this case. X equals C if f of x, which is every other y value, is smaller than f of c for every x in the domain, and vice versa for a minimum. So as I said, it would be the largest or the smallest value of y in a given interval compared to everything else. So here in the next slide, I have a little example, just easy example. You can eye it out and find out what the maximum minimums are. I don't think you should take a second and solve this one because let me explain first and then you can do something a little bit more tough. Find the absolute minimum and maximum between 0 and 2 inclusive in the graph of x to the power of 2. So this is the graph of x to the power of 2. And I'll give you a small hint. There are no local maximum minimums because you really don't have any local maximum minimums. I will explain why in the next graph. So finding the absolute maximum. Let's find the minimum. So you look at this graph and you look at the smallest. Where does the graph cross the smallest value of y? And it's 0, 0. Same thing for the maximum. Where does the graph max out? Basically, it's at 2, 4. Let me tell you another thing. If you notice here, 0, 0 is actually also a critical point. Because if you remember, I told you that when the graph has a valley and kind of like this tops up upside down in the case of a valley or tops up in case of a hill. So here, this is also a critical point. I will explain them in more detail in a little bit. So let me just read the slide. The absolute min and max between 0 and 2 inclusive in the graph of x to the power of 2 are the maximum is x equals 2, y equals 4. The minimum is x equals 0, y equals 0. In the domain 0 to 2, the 2 points mentioned are max and min as per the definition. The 2 points are the largest and smallest values of y respectively. Let me add, respectively, in the given domain, like in the whole given domain. All right, let's take another example. Another graph. Let's try and solve this one. This graph is a little more complex than what I showed you before, so it's probably going to have a bunch of local maximums, local minimums, absolute maximums, and absolute minimums. So let me read out the question. Let's find all the extreme points in the interval -1 to 1 inclusive for the graph of x to the power of 3 plus x to the power of 2. So looking at the graph, what can we decipher? This is, of course, in the exam, you're not going to solve them. Most likely, you're not going to solve them like this. There's more work, but I'm going to show you in a minute how to solve it mathematically. I just want the concept to, stick. Or what's the word? Let's bring the concept home, basically. Let's look at this graph, and first of all, let's find absolute maximum minimums, because usually these are the easiest ones to decipher if you're just looking at the graph. If you remember, absolute maximum minimums are the largest y values throughout the whole domain, or smallest y values, respectively. Smallest y values or largest y values throughout the domain. Commonly, this is not always the case, but commonly they might be the extremities. So the maximum extremities of a graph. So the last interval, the start and end of a graph. So looking here, as I said, 1, 2 would be the absolute maximum of this graph. You see here? It's the absolute maximum because it's the largest y value within our working domain. And -1, 0 is going to be, oh, look here. There's a wrench in our methodology. -1, 0 is the smallest value in the y domain. But if you look here, 0, 0 is also the smallest value in our domain. So that's interesting. And yes, you can have more than one absolute minimum, as I've stated here. So yeah, we just found 2 absolute minimums, which is again possible. Moving on to local and maximum minimums. Local maximum and minimums. What was the definition of local maximum minimums? It was that if you see a point that is, let's say, unlike the other points, or it's the maximum of a group of points when there's a change in the graph, so like a curve in the graph. The maximum, local maximum is usually, not always, usually a critical point in the graph. So let's find a bunch of critical points here. If you notice, you'll see here that I think this is a 2 by 3. 2 by 3 x is a critical point where the graph hills. It pops up where it has like a hill. It goes up and then goes down. So naturally, it's going to have some natural maximum at that tip. Same thing with this valley at 0, 0. You will have a valley with an upside down tip. And there you're going to have some kind of minimum value. I will show you how to find this in a minute. So really, we realized that -2 by 3 and 0.148 is a maximum value within this small range of it. So it's going to be a local maximum. It's not larger than 2, but it's a local maximum. So a relative maximum. It's a maximum relative to its position or the y values around it. 0, 0 is also a local minimum because relative to the points around it, it's actually the minimum. So it is a local minimum. -1 and 0 is not a local minimum. Now that you understand how to find points like local mins, absolute mins, critical points by eye, so you can see them and see like a hill, valley, like hill, valley, critical points, extremities, most likely extrema, so maybe minimum, maybe maximum, maybe neither. But now you know how to look at a graph and decipher these points. They're extreme points. Let's find out how you can mathematically find them through like having just a function without a graph. Well, you can have a function and a graph or just a function, but I'll show you how to decipher it. Anyway, there are three simple steps that you have to take to find out your minimum maximum values in a graph. The first step is find the derivative of your function f of x. To begin, we simply find the derivative of the function you are given. Why? Well, it ties into step 2. You have to find the derivatives of the given function that you have because you need to find the critical points. Step 2 states find critical points. Next, we find the critical points of said function. Remember, a critical point is when the derivative of f of x is equal to 0 or the derivative of f of x does not exist. So this is us finding hills and valleys in a given graph to decipher whether or not they're minimums or maximums. Step 3 here is kind of trial and error. Okay, so what you're gonna do, let me read out. Test interesting x values. So anything you find, any interesting values. There's a list of interesting values. You don't just look at an x point and say it's interesting. No, here, well, you can, but some of them are more interesting than others, and there's a rule that they follow. So test interesting x values. Finally, we plug in numbers of interest into our original function f of x. Then we compare y values. Okay, interesting x's include the ends of our intervals and critical points. Also, don't forget to try 0. So let's look at our old graph, right? So let's say, for example, we were taking this procedure to our previous graph. First, we would find the derivative of this function, right? And then we would find the critical points. The critical points are going to show up as -2/3 and 0. And then in the final step, we would plug in -1, we would plug in 1, we would plug in -2/3, and we would plug in 0. And in the end, we'll find all our points. So you don't need your eyes, you just need a little bit of math magic, if I say so myself. Let's see here. This is an example that we're gonna solve mathematically. I encourage you to take a couple minutes, solve it. It's simple-ish and it nicely follows our steps. So just take step 1, 2, and 3 and apply them to this function. You have the function and the interval. So find the absolute and local min and max values for the graph of x to the power of 3 minus 3x plus 2 for the interval -3 and 3. Hint, if you haven't paused me yet, again, let's go over the steps. First, you'll find the derivative, then you'll find the critical points, and then you would test the critical points and the extremes being -3 and 3. Okay, hopefully you're back. And let's see what we've worked out here, okay? Don't look at the final answer, just follow my mouse as we solve this together. Since f of x equals x cubed minus 3x plus 2 is a cubic polynomial, we conclude that f of x is continuous in the interval -3 and 3. This is something you learned in derivatives, where you can't find the derivative of a function that is not continuous, right? So you have to state this for marks, I believe. I wrote the exam a while ago, so I think this is how it is now. So we take step number 1. The derivative of x is equal to 0. You want to solve for the derivative of x equals 0. First, you find the derivative, and then you solve for 0. As we solve, we discover that the function has two critical points at x equals -1 and 1. So you have your two critical points. Write them down so you don't forget them. Step number 2. Find critical points. Yeah, we did that. We found -1 and 1. First, we found the derivative, which is 3x squared minus 3 equals 3x minus 3 is our derivative. And then step 2, we equate it to 0, and then we find the critical point. And then, let's see here. Based on the information below, let us find absolute max and absolute min, local max and local min. So if you remember step 3, we need to plug in all our interesting x points into our original f of x. So we start with, well, here I started with -3, beginning with the interval, and we found that at -3 the value of y is -16. And then we plug in one of our critical points, why not? And we find out, so we replace -1 in the x's here, okay? We found out it's equal to 4. And then we plug in 1, which is our other critical point, and we found out it's equal to 0. We plug in 3, which is our other extreme. If you see here, it's the other end of the interval, and we found out it's equal to 20. So what does that tell us? Again, what I said was your extrema or your mins and maxes are usually going to be at the end and at critical points of your graph. If they give you the graph, you can decipher it. You can just look at these x's and then see where the y's end up, or are they maximums. So let's go back to the graph before we look at these answers. Let's go back. So first things first, we have -3 gave us -16y. So we go to -3 and then we realize -16. -16 looks like the absolute minimum of this graph because it's the lowest value, and it's also at the extreme of our interval, which is neat. It follows our rule. And then what did we test? We tested -1, which is one of our critical points. We notice here -1 is equal to 4, and comparing it to the y values around it, we notice that it's a maximum. Compared to all the y values here, it's bigger than all of them, which is an inherent feature of critical points. They're usually extrema when it comes to relative, when you compare it to relative points around it. We then tested 1, and then we found that it's a minimum because it's smaller than all the y values around it. And then we test 3. We find out it's equal to 20, and that value is bigger than, firstly, bigger than our local maximum that we found out. So this is the local maximum. It's not an absolute maximum. It would have been an absolute maximum if 320 didn't exist in this case, and this would have been an absolute minimum if -3, -16 didn't exist in this case. So our intervals were smaller. But we have these two extremes, and they're inclusive in our interval, so they are valid points that are bigger than these 2 points, making these only local minimums instead of both absolute and local minimums. So as we see here, the final answer would be absolute max equals 320, absolute min equals -3, -16, and the local max -1 for local min 1, 0. By that, we find out the answer. So hopefully you have a good basis at the derivatives and you find this out. The concept is relatively easy as long as you give it as respectable. You don't give it enough time. Respect the concept. Yeah, it looks easy, but you need to practice, as with all math. And this area of calculus will be used in business. It's used in statistics. It's used in engineering. So don't stock off. Trust me, you will use this. You will need this, whether it's for business projections, optimization problems. If you're engineering, you're going to use this for, speed graphs, like materials, all that stuff, yield graphs. And, I'm an engineer myself, so I expect to use this more often in the future, as you need extremes. Extremes are very important because they tell you something definite about the thing that you're studying. Anyway, this is the end of it. Good luck. Hopefully you found this video helpful, and check out our Math 1500 playlist. We have many videos on different topics and course made by very, very talented people. And again, hopefully you enjoyed this video. Leave a like, subscribe, and thank you. Goodbye.